This is section 2.2 of your MathLinks 8 book. This is on rates. Now, before we were talking about ratios, a comparison of two quantities. And ratios can be things like comparing a whole bunch of dwarves, and some of them have hair and some of them don't. You could say, 6 have hair, 4 don't, so the ratio would be 6 to 4, and so on and so forth. But a rate is a little bit different. It's a comparison of two quantities in completely different units, and that's things like here we have the mass of a black bear at birth, and here we have the mass after 60 days. So a ratio could be something like 0.3 to 0.7. This would be a ratio of black bear birth mass to polar bear birth mass, and we would call this a ratio. But a rate is a comparison of two things that are not the same thing. So in this case, a rate that we're going to make from this table will be a comparison of mass to time. So mass is a measurement of an object's weight, I suppose, and time is a number that is completely different to that. So this is really quite a tricky question. So it says make a rate from this. So days is listed there and the mass is listed here. So if I look at the mass, some people probably did this, 6.5 kilograms over the course of 60 days. This is a show of hand. How many use that as their rate? Did mass to days. How many use something different? How many realize now that's what they should have used? Okay. Now the problem is that number is wrong. Can anyone tell me why 6.5 kilograms is not the number that needs to go up there? Okay, I'll tell you why. Because at birth, the polar bear did not weigh 0 kilograms. At birth, the black bear weighed 0.3 kilograms. And at the end of 60 days, it weighed 6.5 kilograms. So actually, the rate of change in mass was not 6.5 kilograms, but rather 6.3 kilograms. It gained 6.3 kilograms of mass over the course of 60 days. And this we call a rate. This is its rate of growth, 6.3 kilograms over 60 days. But what it says is we want to convert that into a unit rate, which means we need to compare that in terms of 1 day. Okay? We want to know what its growth rate was over each day. So for this one, we're going to take our first and second term of our ratio, divide by 60. When I divide 60 days by 60, I'm going to get 1 day. And when I take 6.3 kilograms divided between the 60 days it was growing, that means it grew 0.105 kilograms per day, or 0.105 kilograms per day. Now that's not quite, just 1 second. I can't subtract. I've been corrected. It's not 6.3, it should be 6.2. 6.2 kilograms of growth over the 60 days. So my division will be 6.2 divided by 60, which is slightly different. It works out to be 0.103 repeating, 0.103 repeating kilograms per day, or roughly the mass of 2 Kit Kats, because 0.103 kilograms is really 103 grams, approximately, repeating per day. A Kit Kat has a mass of about 51 grams, so two Kit Kats worth of mass that polar or that black bear grew every day. And this would be a unit rate. A unit rate because the second term is 1, in this case day. Okay? And there are other ones you could use. Those are just the ones I chose. So the unit rate that describes the bear's growth is 103 grams a day. The rate is 6.2 kilograms per 60 days. That's just a rate. In the second question, 2 brands of canned dog food are on sale. Assuming that the cans are the same size, brand A costs $13.60 for 8 cans and brand B costs $8.75 for 5 cans. Explain how to find a unit price for brands A and B. So the first thing I have to do is ask myself, do I want to know the cost per can or per dollar? And when you say it, you realize you want to know the cost per can, which means your second term is going to be can and your top term is going to be dollars. So for brand A, we have a cost of $13.60 for 8 cans. And since we want to make a unit price, we want to know the price per 1 can. So we think of this just like we would equivalent fractions. If I divide the second term of my ratio by 8 to get 1 can, in order to maintain equality, I would have to divide the top term, which means $13.60 divided between the 8 cans. The unit price is $1.7 or $1.70 per can. I can rewrite that like this, $1.70 per can. For brand B, it's a little bit different. It's $8.75 for 5 cans. So if I get that down to a unit rate, I want to know how much it is per can. So again, I divide both by 5. And $8.75 divided by 5 is $1.75 per can. So the cost is $1.75 per can. So brand A is slightly cheaper. It's a nickel cheaper a can. And because the prices are so close, most people would just go with whatever brand they prefer, A or B. It doesn't matter because the percent difference per can is very little. It's only probably, you know, less than 3% difference in per can. Question 3 gives 2 examples of rates that are common in everyday life. Well, one that I always say is probably the most used is the rate of distance to time, or the rate of speed. The rate of speed. On Granville Street, the unit rate is 40 kilometers per 1 hour is the speed limit. That's an example of one. Another example is if I shop at Bulk Barn and I want to buy my jujubes because they're the freshest. I think they're 88 cents. The cost is 88 cents per 100 grams of jujubes. So it's the best place to get your jujubes if you like jujubes. If you don't like jujubes, don't buy from Bulk Barn. But those are examples of rates you can buy in everyday life. Or another one would be volume. Cost of volume if you buy gasoline. Right now it's $1, I think roughly 5 cents per 1 liter of gasoline. And that would be a unit rate. And if I bought, for example, I filled my gas tank up and it was 52.6 liters, I would be able to multiply this by 52.6 to figure out if I bought 52.6 liters of gasoline, 1.095 multiplied by 52.6 liters, I would know that my bill would be roughly $57.60. Okay, so those are examples of rates that are used in every day. Question 4, determine the unit rate in each situation. So for this one, I'm going to make sure my bottom number is 1. So an orca swims 110 kilometers in 2 hours. I'm going to look at the rate of speed, which is kilometers per hour. So 110 in 2 hours, the unit rate being 1, I would simply divide first and second term by 2. I get 55 kilometers per hour. And that is the unit rate. That's a pretty fast orca. A Canada goose flies 800 kilometers. Again, my top term is distance. My bottom term is time. In 12.5 hours, I would simply divide both by 12.5 to create a unit rate of 1 hour. And in this case, I think it's 37, maybe? 37.5. Divided by 12.5. Oh, 64. I'm way off. So a Canada goose is pretty fast. It flies at a rate of speed of 64 kilometers per hour. I'm sure a lot of that has to do with wind, but the last one is Kathy planting 45 daffodils in 30 minutes. Okay, so again, I want my time unit to be, so I'm daffodils per time. Now the question is, would I rather have how many daffodils she planted per minute, how many daffodils she planted per second, or how many daffodils she planted per hour? Which seems to be the most reasonable time unit to use for my unit rate? Hours is correct. Most of you probably went down to minutes, but you would have had 1.5 daffodils a minute, which really doesn't make sense because you can't plant half a daffodil a minute. It'd be much more reasonable to look at it as being 90 daffodils per hour. That's the rate of speed she plants daffodils. She can plant 90 daffodils per hour. In the fifth question, what is the unit rate of each? So a blue whale eats 8 tons which is 1,000 kilograms. So 8,000 kilograms, or roughly, if I multiply that by 2.2, 17,600 pounds of krill every 2 days. So 8 tons in 2 days. So again, our unit rate can be per 1 day, per hour. Probably for this one, we want it in 1 day, which is pretty easy. 4 tons per day. So 4 tons per day. But an interesting one would be how much does it eat per hour, right? So I could take that day and divide both by 24, and I would get 4 divided by 24. 4 divided by 24 is roughly 0.16 repeating tons per hour. And again, if I think about that as being 1 ton is 2,200 pounds, then if I multiply that by 2,200, it's roughly 366 pounds of krill every hour blue whales eat. That's a lot of krill. But the answer was probably this one here. 4 tons per day is the one that you probably will put if you had a test on it. A blue whale is able to also cruise. I'm assuming that just means speed in water. It's 193 kilometers in 10 hours. This one I can do without a calculator because I'm going to divide both by 10. And I'm going to get 19.3 kilometers because when I divide by 10, I just move my decimal over one spot, in 1 hour, or 19.3 kilometers an hour. And finally, a bull moose bellows 15 times in 2.5 hours. So it's bellows over time. So it's 15 bellows in 2.5 hours. Divide both by 2. You get 7.5 bellows. No, sorry, that's 2.5 I got to divide by. That's not right. So 15 divided by 2.5 is 6. So 6 bellows per hour. Or roughly 1 bellow every 10 minutes. Right? It bellows once every 10 minutes. Question 6 says Gina earned $78 for working 6 hours, and Assad makes $192.50 after working 14 hours. Here is where we see unit rate in practice. If we want to compare who makes more per hour, we can't say just by looking at the rate of pay for 6 hours and 14 hours. We have to examine both of them in terms of what they make per hour for the rate of pay. So Gina is $78 for 6 hours, which means if I divide both by 6, yes, Mr. Valet, that's true. It would be 78 divided by 6, which is $13 per hour. So Gina would make $13 per hour. And Assad would make $192.50 for 14 hours. And therefore, 192.5 divided by 14 would be Assad's hourly rate of pay, which is $13.75 per hour, or $13.75 per hour. So Assad makes slightly more money. Question 7 shows the price difference of for nuts. You have a small bag, which is 300 grams, 500 grams for a medium bag, and 700 grams for a large bag. So the problem is most people probably want to do this. They see this number, they put it on the top. They see this number second, they put it on the bottom. And really, that's not what we want to do. We want to look at price per 100 grams, which means our mass is going to be our bottom number. So for 219, for 300 grams, I can divide both by 3, and I get 73 cents per 100 grams. So if somebody bought that 300 gram bag, it would cost you 73 cents for every 100 grams. That's in nut package 1. In number 2, you have slightly more. You have 500 grams, but it costs you $3.09. So again, I want to divide both by 5 because 500 divided by 5 is 100. And now when I look at it, the quantities I'm receiving in both 1 and 2 are going to be the same. So $3.09 divided by 5 means it's roughly 62 cents. Is that right? Approximately 62 cents per 100 grams. So this is 73 cents per 100 grams. This is 62 cents per 100 grams. And some people still think that 100 grams isn't 1, but it is 1. What's 100 grams really? It's 1 what? No. What is it? Close. We call it decagram. A decagram. Yes, it is. 1,000 grams is a kilogram. 100 grams is actually is a decigram, not a decagram. And the third one, it is per 700 grams, and it's $4.83. So if I divide both by 7, I will create a proportional amount per 100 grams, and $4.83 divided by 7 gives us a unit price of 69 cents per 100 grams. And therefore, when we examine all three unit rates, we realize that 100 grams of nuts in the second package is the best value. And the worst value is the small package. Question 8, we changed the numbers here to represent the cafeteria. This is 237, and it's 80 cents, or 40 cents, sorry. This is 500 mils, and it's 80 cents. And this is 1 liter, and what did the superstore sell it for? $2.30. Okay. So we want to look at cost per 100 milliliters, which means our milliliters are going to be on the bottom. So the small is 40 cents for 237 mils. Now, this is where it gets confusing for some people. Some people have to take it down to 1 milliliter and then take it back up to 100 milliliters. That's okay to do because they realize that if you divide by 237, you get per 1 milliliter. But the only problem is if you take 40 cents and divide it by 237 milliliters, the cost, since this is money right here, the cost is less than a penny. So when you have something that's less than a penny per unit, you need to keep 5 decimal places. So it's less than a penny per milliliter because now, to get it back up to 100, I'm going to multiply by 100, I'm going to move my decimal 2 places over. It's roughly 16.8 cents per 100 mils, or approximately 17 cents for 100 milliliters of liquid if you buy the small milk. Now the medium milk is 80 cents for 500 mils. And I don't need to take this down to 1 because I know that to go from 500 to 100, I can go right away without having to go to 1. I can just divide it by 5. And 80 divided by 5 is 16. So here I didn't need to go this step here. I didn't need to keep my 5 decimal places and take it down to 1. All I needed to do was go right from 500 to 100. And now it's approximately 16 cents per 100 mils if you buy the medium. And finally, the large one, if you went to Superstore, as opposed to the cafeteria, you would pay $2.30 for 1 liter of milk. Now, since we're dealing with milliliters, we have to realize that 1 liter of milk is really 1,000 milliliters, which means I could divide by 10 to get that unit rate of 100 milliliters. And divide by 10. When you divide by 10, you simply move your decimal over. The cost of milk at Superstore for buying the larger container is 23 cents per 100 mils. I must make a confession. Obviously, the best deal is to buy medium milks in the cafeteria. So if you and your family drink a lot of milk, it's best if you buy all of your milk from the cafeteria and take it home. Over the course of a year, believe it, like if you drink 2 liters of milk a day, right? You're saving 7 cents per 100 mils, so 70 cents per liter, $1.40 per 2 liter, $1.40 multiplied by 365 days. Over the course of a year, if you bought your milk in the cafeteria, you would save your family $511 over the course of 1 year, just by switching to buying your milk in the school cafeteria. So if you drink more than 2 liters a day, it's a great deal. Now you know. So the best deal is buying 80-cent large milk from the cafeteria. Mala is shopping for honey. Her favorite brand is available in 2 sizes. So for this one, we're still going to do cost per volume. And the large is going to be $9.59 per 1,000 milliliters, which we know is a liter. Now there's 2 ways to do it. You could break them both down into 100 mils, but that would be silly because one of them is already a unit rate. This one right here is already in a unit rate. It's $9.59 per liter. So all I would have to do is multiply both of these by 4, and I would have a comparable unit rate per liter. So $2.79 multiplied by 4 tells me, but that honey is $11.16 per 1,000. This one is $9.59 per 1,000. So brand B is the better deal by almost $2. Right? Probably about 25% better. 20% better. Trevor rode his mountain bike 84 kilometers in 3 hours. That man is amazing. 84 kilometers is farther than Charlottetown. Probably from here to Tignish in 3 hours. He was trucking along. So 84 kilometers in 3 hours means he had a rate of speed, 84 kilometers, divided by the 3 hours that he traveled. He was traveling at 28 kilometers per hour. Jillian rode 70 kilometers in 2.5 hours, or 2 hours and 30 minutes. So if I divide 70 by 2.5, I get that same unit rate. She also was traveling at a rate of 28 kilometers per hour. So who was faster? Neither. They were both the same. Traveling both with the same speed. Okay, question 11 says, Shannon needs to have a good long look at how much granola bars should cost you, because she pays almost $10 for 12 granola bars. They'd have to be yogurt covered. You buy them? You have money? Oh, where do you get money from? My parents? Oh, okay. I see. So what we want to do is we want to look at this as a price per bar, so per 1 bar. And again, this is a unit price. So I divide the cost of the $9.96 by 12. $9.96 divided by 12 gives me a unit rate of 83 cents per bar. Okay, 83 cents per bar. That's an easy one. And finally, the last question says, the rate at which glaciers melt is increasing globally. The Saskatchewan Glacier near Banff has receded 1.5 kilometers in 75 years. So we're looking for distance to time for receding. The first one is 1.5 kilometers over the course of 75 years. So we're going to see how much it receded per year. And this is the Banff one. The other one, it receded 1,320 meters in, and we have to do a quick math calculation, 70 years. Right between the years of 1923 and 1993 is 70 years. So right off the bat, when we look at our top terms, one is in kilometers and one is in meters. So the first thing you should do is make a quick metric conversion. 1.5 kilometers is 1,500 meters. And now we have 2 rates that when we find a unit rate of per year, they are comparable. So if I take the first one, I'm going to take 1,500 meters and divide it by the 75 years that it took to recede that much. And that will tell me it receded 20 meters per year. Okay? Kind of like my hairline, 20 meters per year. 20 centimeters per year. And in the second example, if I take the distance that it receded over the course of 70 years, it receded roughly 18.9 meters over the course of that 1 year. So the first one, the Saskatchewan Glacier, was receding at a faster rate than the second glacier, the Peyto, which was receding at 18.5 meters per year.